Alright guys and gals, so we're going to try something new today. Let's see if this works. So as to try to save my voice a little bit here, hoping to use this as a way to help get me through the day without relapsing and not being able to talk at all tomorrow, we're going to try today to do alternate form of the derivative, but with Sick Edition, aka with the help of this lovely app that I found. I'm going to try to make it so I only have to say this once, as opposed to 3 times in the day. And not only that, but we'll post up on the web and you can listen to my lovely croaky voice anytime you want. As a reminder, the homework tonight, of course, is the worksheet. And also, quiz is on Tuesday. I think I just put that on the board, but in case I forget to tomorrow morning, that's, now up there now. Although this will probably be very confusing if you're watching in another week. But anyway, Quiz Tuesday next week. Now, moving on. Now, even though, you know, we have this recorded, these examples are from the notes. It's the same as that worksheet you're holding. And, of course, you really want to make sure you're paying attention to the fact that I'll be writing that limit notation every single time. It's not just because I'm obsessive compulsive, it's also because it should be there. You need to make sure that you're always showing that limit notation every single time until you actually take the limit. So, yes, it is true, you need to show that limit every single time. Also, just as an FYI, even though these examples are, excuse me, pre-recorded, of course, just stop me anytime, ask questions. I'm really just trying to save my voice here. As you can hear, I can talk. It's just that I can't talk for very long without starting to cough randomly and, whatnot. But please, stop me. Ask questions if you need. Now, moving on. Here we go. So I've got alternate form. That's what we're getting at today. Now, this is great because while it's a little faster, it has this problem, and that is the fact that it can only be used to find a single point's derivative or slope. So here's that formula. It's on your note sheet there for you. Notice it's just like any other slope. It's a y minus y over x minus x. The thing is, though, in this case, it's talking about one specific point, and that point is this point c in that formula, or c comma f of c if we're really talking about the point. So that means that when we're using that derivative process, we have that one fixed point, and then we're using another point, say x comma f of x, and we're dragging that one point over using the limit. So since we're dragging one point specifically over to that x value of c, we're getting one specific slope. So while this is faster than doing the actual definition of the derivative, that's the one from the other day, that's the delta x that's going to 0. While it's faster, it can only give us the slope or rate of change at one point, as opposed to the definition, which can give us a formula for all slopes, which we'll need sometimes. So there's definitely a benefit and a strong, strong, strong importance in knowing the definition. And you want to make sure that anytime you don't just want one specific rate of change, that you use that definition using your delta x. Otherwise, it can really cause some cumbersome problems later on. Alright, so more on that in the future, though. Today is all about the alternate form. So let's see that alternate form in action. So let's say we want to go to that first example and we want to find the oh my gosh, excuse me, the slope at 3. So this is a parabola. Notice I made that little sketch there in orange for you. And I noticed that its slope needs to be positive. So I went ahead and with that sketch, what I did was I allowed myself to kind of get an idea on what the answer should be. I should get a positive number. Even in that really, really terrible sketch, I can tell that that number I get better be bigger than 1, because even though that's not very accurate of a sketch, I can tell already that little red tangent line there definitely is a slope bigger than 1. Notice notation-wise, f prime of 3 is saying that I want the slope at 3. Now, since I just want the slope at 3, I'm going to go the faster route. I'm not going to find the formula and plug in 3. Sure, I could, but I'm going to instead find these slopes specifically at 3 using this alternate form of the derivative. So there's my alternate form of the derivative. I'm going to go ahead and plug in f of x, which is x squared plus 4, f of 3, of course, I get good using good old algebra by plugging in 3. That gave me 13. So when I simplify it, I'd have x squared minus 9, which factors, and that will allow me to simplify and cancel to get the limit as x plus 3 approaches the x of 3. So that would be 3 plus 3, or 6. And yep, that looks about right. It's positive, it's steep, and I bet if I had sketched that on graph paper, it would probably be easily counted out to be up a rise of 6 over 1. And again, notice that notation. F prime of 3 equals 6. I didn't just say 6, I said what that was, and that f prime notation means slope of 3 means the slope at 3, or rate of change at 3, is 6. Alright. So now, let's talk about how I can tell if a derivative exists, meaning if a picture actually has a slope or rate of change at the spot. Now, not every single picture has a slope at a particular spot. So what you see here in your notes is talking about when does a derivative exist. Well, a derivative exists if and only if we have the slope from the left. Notice that notation is talking about the limit from the left, and that's a slope, y minus y over x minus x. So if the slope at c from the left and the slope from the right at c, so notice that little plus sign there, if those two slopes are the same value. So in other words, if the two one-sided limits agree, then this derivative would exist. So as long as these two are equal, I will have proved the existence of the limit. Of course, that means the other way is also true, in that if I show that the one-sided limits are equal, then the derivative exists. But if I show that they do not equal one another, or that one of them does not exist, then the derivative would not exist. Alright, now what we're going to do in these next three examples is we're actually going to prove the three different places where a derivative doesn't exist. There are three different things that you can actually look and see in a picture that will allow you to know immediately that a derivative doesn't exist. Now, of course, if we're asked to prove it, which is what we're going to be doing in these three examples, if we're asked to prove, well, that means we actually have to show it. So that means that our work, of course, is going to be important. So in this first example here, I'm going to use one-side limits. That's always what I use if I'm trying to prove that derivative doesn't exist. And I'm going to prove that the slope or derivative at 0 does not exist for the step function. Alright, so now let's go through what I need to do. Well, I need to find the limit from both sides. So I'm going to find the limit of the slope as I come from the right. So that means I'll be finding the right-handed slope. Now, what you saw here is I took the alternate form, because I'm only talking about the slope at 0. The alternate form is the easiest, most effective way to prove the non-existence or existence of a derivative or rate of change at a point. So, there was my y minus y over x minus 0. So, of course, f of 0 gave me the step function of 0. Step function of 0. 0 is an integer, so it came out as 0. That gave that simplified expression you see before you. Now, I'm coming from the right, and it's a step function. So if you remember back to the last unit when we were working with limits, if we want to come from the right, that means that what we did to evaluate a step function coming from the right is we thought of a value very close to 0, but on the right, so it's positive. 0.001 is a decimal. It's going to round and be pushed down to the greatest integer below it, so it'd be 0. 0 divided by anything is 0, so that means that the slope as I come from the right would be 0. If you're visualizing the step function's picture, that shouldn't surprise you. Right now, I'm going to figure out what the limit is as I come from the left. Now, the first several steps are going to be the same because it's the same formula. It's just f of x minus f of 0 over x minus 0. So we had already found that. In that yellow circle, you see it there. That would be the step function of x over x. Now here's the thing, though, I'm coming from the left, so you're going to see that we're going to pick a value on the left. That's a little less. That would be a negative this time, 0.001. Now I'm going to plug that in there, but remember that the greatest integer function pushes things down to the next greatest integer below it. So it'd be a negative 1 divided by a negative 0.001. But here's the thing, I know that equals a number, and that number definitely isn't 0. But conceptually, remember that we picked that red number there to, as kind of like a table of values process, find something as we head towards 0. And the closer and closer we get to 0, that would be going to -1 over 0, because remember I'm heading towards 0. So I'm not going to say that that slope is heading towards 1,000. I'm going to say that slope doesn't exist, because it's actually heading towards -1 over 0, so it's heading towards an asymptote. It's trying to go perfectly vertical. Now either way though, we have the right side slope heads to 0, the left side slope doesn't exist as I head towards it, so since the slope from the left doesn't exist, much less it doesn't equal 0, the derivative at 0 doesn't exist. Now let's look visually at the picture. So it's a step function. And I know what you're thinking. You're thinking, well, each of those steps is flat. The slope should be 0 from the left and the right. But here's the thing. Remember that we're trying to attach to that point 0, 0. So as I try to connect those points from the left, I'm trying to attach a point up to the origin. And as I get closer and closer, I'd be heading straight up. Now, in the picture, what we're looking at is a break. Any and every discontinuity doesn't have a slope. If there is any kind of discontinuity at all, you immediately know the derivative doesn't exist. Now, of course, if you're asked to prove it, you can't just say, oh, it's broken, I've proved it. No, no, no. You identified a shortcut that allowed you to know. If you're asked to prove, you have to show your one-side limits. There's no way around it. You have to show the work for the two sides, identify what the two sides are heading towards, and identify if they're the same or different. All right, let's see a couple other examples here. So example 2, we're going to prove that the derivative at 0 does not exist for the function x to the 1/3. All right, so same thing, I want to prove it. So what am I going to do? I'm going to find what the limit is coming from the right. I'm going to use my alternate form because I only care about 0. Coming from the right, I end up getting x to the 1/3 over x. So I subtracted using my algebraic properties for my exponents, and got 1 over x to the 2/3. Plugging in 0 to evaluate that limit, 1 over 0, why, by golly, that does not exist. We have an asymptotic expression, meaning that the slope is trying to go straight up to get that asymptote, or this, again, the idea of it heading towards the vertical. Alright, well that's all well and good, but I need to prove the two sides. So let me go to the left. It starts out the same way. So again, I can go straight to, in the second case of identifying that's the same, it's going to be the limit as x approaches 0, this time from the negative or left, of 1 over x to the 2/3. I don't need to re-show those above two steps. I can go straight to that circle value since I've already proven what that was. Now, again, I have 1 over 0 coming from the right or the left. It's not a step function, it's just a regular x raised to a power, so 0, either from the right or the left, plugged in, will give me 1 over 0. In both cases, though, it doesn't exist. So even though the right and the left side are heading to the same concept, that concept is a undefined slope. So even though both sides head to that same thing, that thing, again, it doesn't exist. So hence, the derivative at 0 also does not exist. Now again, I need to show both sides. I was asked to prove that it doesn't exist. That means I need to prove the two sides. Even if I know right away after the one side, I need to show both. The formal definition of a derivative not existing is that the two sides are heading to different values or do not exist. So if you're formally proving, yes, you need to show both sides. Now let's look at that picture to see what shortcut we can identify. Visually, if we're not asked to prove and we're just asked where. Alright, well, x to the 1/3, if I were to graph that, it looks like that purple expression shown. Now notice that at 0, that expression has a vertical tangent line. Well, if your picture is going vertical, well, by golly, a vertical line's slope is undefined. Hence, if the slope is undefined, it's not existing. So there's the second spot. The first spot was any kind of discontinuity. The second spot is a vertical tangent line. And again, if you're asked, where does the slope not exist, you can use those shortcuts. But if you're asked to prove the non-existence, well, then you have to use the two-sided limits. All right, there's one more case here, so let's look at this as last example. So, excuse me. Let's say we wanted to, in this last example, prove that the derivative at 2, in other words, the slope at 2, does not exist for this absolute value function. Okay. Here we go. You can do it, little voice. I think I can. Alright, so we're going to go from the right. The slope from the right of f of x minus f of 2 over x minus 2. That's the alternate form again, because I just care about 2. I plugged in f of x, then I plugged in 2 to find f of 2, and that gave me that simplified expression. Now it's an absolute value. We learned last unit that if we want to evaluate an absolute value from one side, we need to identify whether the expression stays the same or switches. Well, coming from the right, that'd be a positive, so it'll stay the same. So that's what I'll do. I'll keep x minus 2 the same, and ooh, that's 1. And the limit of any constant, in this case the limit of 1, is 1. So this is saying the slope as I come from the right is 1. If you're thinking of the picture of the absolute value, that should make sense. Now let's see what happens from the left. Again, if you're thinking of the picture, you might already kind of know what we're about to get into. Alright, but let's actually prove it. That was the request. So I'm going to take the limit as we come from the left. So remember what we did before. This expression is the same as what we started with. So we can skip that middle step there. We can go straight to identifying the simplified expression of x minus 2 over x minus 2. Forgive me, the upper one was an absolute value. Anyway, it's written right, so that's good. So now though, I'm coming from the left. I'm coming from the left will switch it because I'll be putting in values that are lower than 2. So it would need to be switched. That means that that negative, or opposite of x minus 2 over x minus 2, will simplify to negative 1. The limit of negative 1, no matter what I'm approaching, will be negative 1 because it's a constant. Again, if you're thinking that picture, that should make sense. So the limit from the right, or the slope from the right, was 1. The slope from the left was negative 1. They're different. So since the slope from the left does not equal the slope from the right, the limit of the slope, in other words, the slope itself, f prime of 2, does not exist. Now here comes the last visual shortcut. If we weren't actually asked to prove it, if we were just asked where does the slope not exist, think of the picture. An absolute value has a sharp point. In this case, the sharp point's at 2. In that picture, we can clearly see the slope on the right is going up. It's a slope of 1 to 1. From the left, though, it's going down. It's a slope of negative 1 to 1. So, the slope doesn't exist at a sharp point. That's our third location. Alright, so now again, if we're asked to prove all this work, yes, is needed, mandatory. When we're asked to prove, that means we have to show it. If we're asked to show it, that means we need to prove it. We need to show those two sides. And again, remember, I'm showing that limit notation every single time until I've actually taken that limit, until I've plugged in my value or done some process to identify it. Then I drop that limit notation. Alright, so let's recap here. We've seen 3 examples of proving that a limit doesn't exist. Now let's look for, conceptually, where does the limit not exist? Alright, well, to conclude, our derivative does not exist at a particular location C when one of 3 things happen. First, when there is a discontinuity of any kind, the slope or derivative does not exist. So one example might be a step function. In that step function, at every integer, the slope doesn't exist, but that does not mean the slope does not exist everywhere. There is a slope at 1.5, there's a slope at 1.9, there's a slope at 2.2. At all of those places, we're on a flat step. There, the slope would be 0. We're just talking about where the discontinuity is. Alright, so if there's a discontinuity, there is not a slope there. The second location would be there is a vertical asymptote or a vertical tangent line. If your expression is going vertical, in other words, if there is a vertical tangent line, then the derivative would not exist. So our second bullet there, if you have a vertical tangent line, the slope doesn't exist at that location, but it does exist everywhere else. And of course that last situation in which the derivative does not exist is any kind of sharp point. For example, that absolute value we just saw. There the derivative or slope doesn't exist. Now again, the slope exists everywhere else. However, at that point where the absolute value is turning around, there the derivative doesn't exist. If I were asked what's the derivative at 5, then that derivative would be 1, because the slope is 1. If I was asked what's the derivative at negative 100, well then the slope would be negative 1, so the derivative of that location would also be negative 1. Alright, now, one last thing though about sharp points, there are actually two kinds. There's a sharp point that is created by curved things coming together, and there's a sharp point created by straight things coming together. If you have curvy things, either one curvy or two curvy things coming together, it's called a cusp. So be it kind of like a little elementary school flying bird, or if it's just one wing and then a straight line, going with that flying bird, very, well, again, rudimentary flying bird drawing, both of those are cusps. If it has a curvy piece creating a point, it would be called a cusp. If it's just two straight lines coming together, creating a point, that would be called a node. And again, notice it doesn't really matter what kind of angle is being formed, obtuse, acute, as long as it's a change in slope, some short point, it would be considered a sharp point, even if it's not so sharp. So sorry. So those are two kinds, or two categories. Now, if you're asked to classify which kind of sharp point it is, that's the only time you need to identify if it's a cusp or a node. Both of them, of course, don't have a derivative. So those are our three shortcuts. Now, in your homework, if it asks you just where does the derivative not exist, you can just look at the picture and tell. If it asks you to prove whether or not the derivative exists, then you have to show that work. All right. Now, let's finish out here with a couple true and false questions. Just kidding. Pre-recorded this. Before we get to the true and false questions, first things first, let me just one more time remind you, in order to prove it, you have to use one-sided limits. One downfall to pre-recording something that's about 20 minutes long. Sometimes you forget the slide in between. Anywho, remember again, if we need to prove the derivative doesn't exist, use the one-sided limits. You absolutely have to. And also, you absolutely have to remember your notation counts. You have to use correct notation. And you always need to make sure you're showing that the limit notation... I forgot a T there. Huh. Imagine there's a T in that notation. But you always need to make sure you're showing your limit notation until you take it. Alright, now let's get to those true and false questions. Okay, so now, in calculus, continuity and differentiability will be very important. But it's important also to know the connection between the two. So, true or false? If a function f is continuous at a point c, then the derivative must exist at c. Well, just because it's continuous does not mean that it has to be differentiable. Think of your absolute value. Think of your x to the 1/3 graphs. Both of those were continuous, but in both of those cases, they were not differentiable at those locations. One was going vertical and had an undefined slope. The other came to a sharp point, so the slopes were different on the two sides. Now let's look at the other direction. True or false? If a function f is differentiable at c, then the function f must be continuous at c. Well, if it's differentiable, that means it can't be in those three categories. And one of those categories was any kind of discontinuity. So if it is differentiable, then yes, it must be continuous. Because if it was not continuous, it could not have been differentiable. So it's important to know those connections. While there is a connection in that if something is differentiable, it must be continuous. It does not go the other direction. Continuity does not guarantee differentiability. So you can't just prove something's continuous in order to decide if it's differentiable or not. And we'll be looking a little bit more into that later on in the unit. Now, excuse me. Now remember, this video I'll post up online so you can kind of use it to kind of rehash back both my sickness hopefully this will pass quickly, um, as well as the important points. Remember, of course, for tonight, though, your homework is just that worksheet. We'll actually have some time here to start it, most likely, since this has only been about 25 minutes. And unless we had to pause several times for questions, there's probably about, oh, I don't know, 15 or so minutes left in class. So you'll be able to get a jump start on that, again, assuming whether or not there were lots of questions and we had to pause this along the way. Also, remember that if you're watching this live in class, that means the quiz is on Tuesday. If you're watching this in exam review prep or anything along that line, then maybe there is not a quiz on Tuesday. But for us today, live in class viewing, the quiz is on Tuesday. Again, homework tonight, day 3. And on that note, I'm going to stop talking for the rest of today. And I guess I'm seeing you now, but I really want to say see you tomorrow because this was yesterday. Interesting conundrum. Never done this before. Let's see how it works out. All right. Toodaloo.